When you look up at the night sky on a clear evening, you might spot a faint smudge of light in the constellation Andromeda. That tiny blur is actually an entire galaxy containing roughly 1 trillion stars, sitting 2.5 million light-years away from Earth. It's the most distant object you can see with your naked eye, and it represents our closest large galactic neighbor. But here's the humbling truth that astronomers have discovered. Despite all our technological ambitions and dreams of exploring the cosmos, humanity will almost certainly never reach another galaxy. Not because we lack imagination or determination, but because the universe itself has set up barriers that even our most advanced future civilizations may never overcome. To understand why intergalactic travel remains forever out of reach, we first need to grasp the truly staggering distances involved. Our home, the Milky Way galaxy, is already incomprehensibly vast. It spans roughly 100,000 light-years from edge to edge, containing somewhere between 200 billion and 400 billion stars. Light itself, traveling at approximately 186,000 miles per second, takes 100,000 years just to cross our galaxy. But the Milky Way is merely one island in an ocean of cosmic emptiness. The Andromeda galaxy sits approximately 2.54 million light-years away. To put this in perspective, if we scaled down the distance between Earth and our Sun to just 1 meter, Neptune would be about 30 meters away. On that same scale, the Andromeda galaxy would be positioned roughly 15,500 miles distant. The fastest spacecraft humanity has ever built is Voyager 1, launched in 1977. It moves at approximately 17 kilometers per second, which sounds incredibly fast until you realize this represents only 0.006% of the speed of light. At this velocity, Voyager 1 would take over 40 billion years to reach the Andromeda galaxy. That's nearly 3 times the current age of the entire universe. Even our most ambitious proposals for future propulsion fall dramatically short. The Breakthrough Starshot initiative envisions using powerful lasers to accelerate tiny light sail spacecraft to roughly 20% of light speed. At that velocity, these probes could theoretically reach our nearest star system in about 20 years. But even traveling at 1/5 the speed of light, the journey to Andromeda would still require over 12 million years. The challenge isn't just about building faster rockets. The fundamental laws of physics themselves present obstacles that may be insurmountable. According to Einstein's theory of special relativity, nothing with mass can accelerate to or beyond the speed of light. As an object approaches light speed, its mass effectively increases, requiring ever more energy to accelerate further. Time dilation occurs, meaning time passes more slowly for the traveler relative to stationary observers. These aren't just theoretical concepts but proven physical realities confirmed through countless experiments. From the perspective of someone on a spacecraft traveling at near light speed, the journey to Andromeda might seem to take only decades due to time dilation. But for everyone else in the universe, millions of years would still pass. The travelers would arrive to find that everyone they knew had been dead for eons. But even if we somehow solved the propulsion challenge and found a way to travel at speeds approaching that of light, we would still face an even more fundamental barrier. The universe is expanding, and crucially, this expansion is accelerating. This discovery earned 3 physicists the Nobel Prize in 2011. The expansion of space means that distant galaxies are moving away from us, and the farther away they are, the faster they recede. This cosmic expansion is described by Hubble's law, which states that the recession velocity of galaxies is proportional to their distance from us. The Hubble constant tells us that for every 3.3 million light-years of distance, galaxies are receding an additional 70 kilometers per second faster. This creates what physicist Avi Loeb has called a cosmic horizon for intergalactic travel. According to his calculations, a spacecraft launched from our galaxy could only reach galaxies that are currently receding from us at less than half the spacecraft's own velocity. Imagine running on a treadmill where the belt speeds up the faster you run. No matter how fast you go, you can never reach the end if the belt accelerates quickly enough. That's essentially what happens with cosmic expansion. The space between us and distant galaxies expands faster than we can traverse it. For every billion light-years a galaxy is currently away from us, we need an additional 7% of light speed just to counter this cosmic expansion. The situation becomes even more challenging when we consider dark energy, the mysterious force driving the accelerated expansion. Current measurements suggest that cosmic expansion will be exponential in our future. This means that regardless of how fast we launch a spacecraft, it would never catch up with galaxies beyond a certain distance. As Loeb demonstrated in his research, once the universe ages by a factor of 10, even a spacecraft moving at the speed of light will not be able to catch up with any galaxy beyond our own. The cosmic horizon is shrinking. Galaxies that are theoretically reachable today will become forever unreachable as cosmic expansion accelerates. This fundamentally constrains us to what astronomers call the local group, a collection of galaxies bound together by gravity. The local group includes our Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and about 50 dwarf galaxies, all contained within a region roughly 10 million light-years across. These galaxies are gravitationally bound to each other, meaning they're not being pulled apart by cosmic expansion. Everything beyond this local cluster is receding from us. Even if we could achieve velocities of several percent of light speed, cosmic expansion makes these destinations effectively unreachable. Interestingly, our own local group is destined for a dramatic transformation. The Andromeda Galaxy is currently approaching the Milky Way at approximately 110 km per second. This might seem to contradict what we've said about cosmic expansion, but galaxies within the same gravitationally bound group are not affected by expansion in the same way. Their mutual gravitational attraction overcomes it. Current predictions suggest that Andromeda and the Milky Way will collide in approximately 4 to 4.5 billion years. When this happens, the two galaxies will merge over several billion years to form a giant elliptical galaxy nicknamed Milkomeda. Individual stars are so far apart that actual stellar collisions would be extremely rare, but the galaxy's shapes would be dramatically distorted and new stars would form from compressed gas clouds. Some scientists have proposed theoretical concepts that might allow for faster-than-light travel. The Alcubierre drive describes a hypothetical way to warp space itself, contracting space in front of a spacecraft and expanding it behind. The ship wouldn't move faster than light locally, but the manipulation of spacetime could allow it to effectively traverse distances faster than light could in normal space. Similarly, wormholes might theoretically provide shortcuts through spacetime. However, both concepts face enormous practical challenges. The Alcubierre drive would require exotic matter with negative energy density, something we've never observed and may not exist. Wormholes, if they exist at all, would likely be incredibly unstable. These aren't just engineering challenges but represent fundamental questions about physics that we don't yet fully understand. Another speculative idea involves hypervelocity stars, rare stars that move faster than the escape velocity of the Milky Way. First theorized in 1988 and observed beginning in 2005, these stars achieve incredible speeds through interactions with supermassive black holes. They typically travel at around 1,000 km per second. In theory, a spacecraft could orbit a hypervelocity star and ride it into intergalactic space. However, even at 1,000 km per second, the journey to another galaxy would take nearly a billion years. We would have no control over the direction, merely following wherever the star happened to be going. The time scales involved raise profound questions. If a civilization launched a spacecraft on a journey taking millions of years, what would become of the travelers? Generation ships are a common concept in science fiction, but maintaining a stable society over such time span seems nearly impossible. Would the travelers even remember Earth by the time they arrived? Would they still consider themselves human? The psychological, social, and biological challenges might be just as insurmountable as the physical ones. The energy requirements are also staggeringly prohibitive. Chemical rockets are woefully inefficient. Even antimatter engines, which represent 100% efficient matter-to-energy conversion, face the challenge that antimatter is extraordinarily expensive and difficult to produce. Perhaps most sobering is the realization that this cosmic isolation is not just humanity's fate, but potentially the fate of every intelligent civilization in the universe. If the laws of physics apply everywhere equally, then alien civilizations in other galaxies face exactly the same barriers. Even civilizations millions of years more advanced than us would still be constrained by the speed of light and the expansion of space. The universe might be filled with isolated islands of intelligence, forever separated by uncrossable gulfs of expanding space. There is a certain melancholy beauty to this cosmic isolation, but also perhaps a hidden wisdom. The limitations imposed by cosmic expansion might encourage us to focus on our immediate cosmic neighborhood. We are gravitationally bound to our local group, and these are the only companions we will have for billions of years. Instead of mourning our inability to reach distant galaxy clusters, perhaps we should appreciate the incredible richness within our own galactic neighborhood. The Milky Way alone contains hundreds of billions of stars and potentially trillions of planets. Our galaxy could occupy humanity for millions of years of exploration without ever needing to leave it. The eventual merger with Andromeda will create an even larger cosmic home containing over 1 trillion stars. That's more than enough cosmic real estate for any civilization. Furthermore, our cosmic isolation might actually be beneficial. The farther we are from sources of intense radiation like quasars and gamma-ray bursts from distant galaxies, the safer our local environment becomes. The quiet isolation of our local group provides a stable, relatively safe cosmic environment where life can flourish over billions of years. Understanding that we cannot leave our galaxy should fundamentally reshape how we think about humanity's long-term future in space. The dream of spreading across the universe and visiting countless galaxies may be just that, a dream that physics itself forbids. But this doesn't diminish the profound significance of space exploration. Even confined to our local group, the opportunities for discovery and expansion are essentially unlimited. Within just the Milky Way, there are more star systems than we could visit in millions of years. There are worlds to terraform, resources to utilize, and potentially other forms of life to discover. The story of why we will never leave our galaxy is ultimately a story about the nature of the universe itself. It's a universe governed by fundamental laws that set absolute limits on what is possible. These limitations aren't failures of human ingenuity. They're fundamental features of reality that even the most advanced civilizations must accept. The speed of light is not just a speed limit, it's a fundamental constant woven into spacetime itself. Cosmic expansion is not something that can be circumvented, it's the universe evolving according to its own nature. Yet there's something almost poetic about our cosmic situation. We live in a galaxy bound together by gravity, populated by hundreds of billions of stars, destined to merge with its neighbor to form something even greater. We have billions of years ahead during which our descendants could explore every corner of the Milky Way, could potentially encounter other forms of intelligence if they exist nearby, could build civilizations on countless worlds. All of this is possible without ever leaving our galaxy. The Milky Way is simultaneously our home and our prison, but it's a prison so vast that we could spend eternity exploring it. The universe has taught us that we are both incredibly significant and incredibly small. We cannot leave our galaxy because the universe itself says no. The space between galaxies is expanding too fast, the distances are too great, the laws of physics are too constraining. And perhaps that's okay. Perhaps being citizens of a single galaxy is enough. Perhaps the real message is about appreciation. We should value and protect our cosmic home, explore it thoroughly, and recognize that even within these boundaries, the universe has given us more than we could ever fully explore. This is our galaxy, our local group, our cosmic destiny. We will never leave it, but we were never meant to. The Milky Way is where our story began, where it continues, and where it will end. And that story is still a story written among the stars.